we are finishing up how we are manipulating glucose other than the glycolysis. And so we saw the pentose phosphate pathway. We saw gluconeogenesis. We are looking at how glycogen or glucose is stored as glycogen and degraded. So we're going to synthesize and degrade it. Then we're going to take a look at its regulation of how we do those. And so going back just a few points, we have glycogen, and glycogen is a very large polymer that has lots of alpha-1,4 bonds, but every so often, about on average 10, we have an alpha-1,6 branch point. And what we want to do is we want to release glucose from these storage molecules, and since it has a number of ends, actually thousands of ends, an enzyme called glycogen phosphorylase, or what we call phosphorylase, uses inorganic phosphate and reacts with the ends of all of these branches, and by using the inorganic phosphate releases glucose 1-phosphate. Glucose 1-phosphate is not an intermediate of glycolysis, but using the enzyme glucomutase, we can get glucose 6-phosphate. And so that enzyme will work. It produces a glucose that has a phosphate on it without using the ATP molecule. And phosphorylase will work on every end and produce a lot of glucose 1-phosphate very, very quickly. But once it gets within 4 residues of an alpha-1,6 linkage, it stops working because it doesn't fit into the enzyme anymore. The substrate can't fit into phosphorylase. But it can fit into a deep branching enzyme that has 2 activities. One is a transferase, and it takes 3 units of glucose, transfers it to another end, leaving the single glucose in the alpha-1,6 all by its lonesome. The second activity that it has is to remove that 1 glucose, and consequently comes off as glucose without a phosphate. At this point in time, that's a little bit not as efficient, and what we do is we have to use an ATP to phosphorylate that to get it to glucose 6-phosphate. What enzyme will phosphorylate that glucose? It's a kinase. Which particular kinase? Hexokinase, the hexokinase of glycolysis. Okay? And so it can then be placed into the systems of how we break down glucose. Okay? Because we have all those branch points, we show a burst phase of production, and then it slows down. The reason is phosphorylase is fast, deep branching is slow. In any process in which you have multiple enzyme steps, okay, the slowest step overcomes or takes over the rate. But because there are so many ends beginning at the beginning, the production of glucose over time, phosphorylase, you see only the rate of phosphorylase because it's got so many places to actually react. And then it stops and continues the production of glucose at a much slower rate. The much slower rate is now based upon the rate of the deep branching enzyme, which is much slower. Physiologically, this is important. What would this burst phase allow for in a physiological or real sense, in real life? What might this give an advantage to? Being able to move quickly. The lion coming at you. It burst a lot of starting material for breakdown for glucose, but The rate limiting step also then allows a much slower release over time so that you don't use and overuse all of your fast energy sources, because the burst is going to really overwhelm how fast you can break it down. It's going to give plenty of glucose that can be broken down, and then later we can access your stores at a much slower rate so that you can go longer and really get away from the line. Okay? So, it accounts for the fact that the muscle can sustain maximum effort for just a few seconds only. Okay? Now, phosphorylase, is much faster than the rate of debranching. Spent all that time, and there's a slide right there for it. Okay? And the strategy is that I access enough energy very quickly, but don't use up all of my energy. My daughter just texted me, or tried to call me in the middle of class. All right. Now, what was released was glucose 1-phosphate, okay? And that's what's produced from glycogen, which is not the glycotic intermediate. We need the glucose 6-phosphate. So let's take a look at that particular enzyme and the mechanism by which it works. Okay. All right. Very similarly, there is going to be an enzyme, the mutase, that is going to be phosphorylated. It is phosphorylated on a serine in the active site. Now, previously in the glycotic intermediate that was a mutase, the phosphorylated intermediate was a histidine. So it doesn't really matter what amino acid was, but the enzyme comes in with a phosphate. The glucose 1-phosphate is in the first position, and the enzyme will have a base that takes the proton, and then the electron pair can attack the phosphate. Every time you attack something that has a pi bond, it must kick up, transition, kick down, and the phosphate is now transferred to the 6th position. I have a bisphosphate intermediate. This is where a three-dimensional reaction is not well done on a two-dimensional slide. What really happens is this phosphate here originally is right next to this hydroxide. When the phosphate is attacked and leaves the protein, there's a conformational change that puts this serine now close to this phosphate, even though it looks very far away. This particular reaction now is, oh my goodness, totally wrong in the book. A base will take a proton, and we always have electrons attack, kick up, kick down, and, oh, I won't do that. I don't put a negative charge. I will pick up a proton to make the glucose 6-phosphate. These are in equilibrium, and depending upon where you need to be driven, you can make the glucose 1-phosphate go to glucose 6, or we can even take glucose 6-phosphate and make it glucose 1, and we will see that when we do glycogen synthesis. Okay? And we know that glucose 6-phosphate is processed in a lot of different ways. There is especially a difference between how liver and how muscle treat glucose. Okay, most of the time, liver will send the glucose out to the bloodstream. Muscle, very selfishly, will take it and degrade it through glycolysis. The other enzyme that we're going to look at in terms of mechanistic qualities is the phosphorylase itself. This is where I'm going to break off one glucose, and it's going to come off as glucose 1-phosphate using inorganic phosphate. Okay? Now, if by chance you have the most simple type of reaction, which is an S&2 reaction, what you could predict is this. The phosphate would come and attack, and this would leave. Well, now that is, it's not H star, it's an H plus. All right. Now, if that did happen, you would have inversion of stereochemistry. And we do not see inversion of stereochemistry. So it is not as simple as this. All right. What has to happen is that the phosphorylase is going to use a cofactor called PLP. We've actually used PLP before. All right, but we're going to use it a little bit differently than what we saw in previous uses of this cofactor. If I actually look at the active site of the phosphorylase, what you're going to see is the lysine that has that PLP, and you're going to see the phosphate right here. This phosphate is what's going to be important of that cofactor. There's a lysine, there's an arginine, and even glycines, the amide or the peptide proton can orient. And what all of these things do is orient the incoming free phosphate, because that's what's going to be part of the reaction. So the PLP is going to help orient and make the inorganic phosphate more reactive. Here's what happens, okay? Another rendering. This is the lysine, this is the phosphate of PLP. It has a proton. Here is the incoming inorganic phosphate. Now when we write PI, what we very rarely or seldom tell you, or even write, is most of the time you're carrying one proton. Okay, so it is written here in that particular form. We've got two negative charges. They are actually resonating. There is one hydroxide. This inorganic phosphate is going to react with both sides of the glycogen chain, the side that falls off and the side that is still the longest chain. And the first thing that happens is the oxygen of the long chain will pick up this proton. And so the long chain now has a free hydroxide, that's here, and I have a sugar that is in the carbocation state. In this mechanism, the phosphate then can attack the carbocation, and the phosphate now retains alpha conformation where the bond between the sugars was also alpha. Now, if you were in an organic flask and you had a carbocation and you have a nucleophilic substitution, because that is a carbocation, it is trigonal planar. That means the phosphate could attack from the bottom and the phosphate could attack from the top, and you would get a racemic mixture. Inside an organic flask, you would get a racemic mixture. Inside an enzyme, retention of stereochemistry indicates you most likely has gone through an SN1 mechanism, which invokes a carbocation, but the attack is only from one side. The reason is this. One, the enzyme physically is binding the active site and blocking one of the sides of that carbocation, and the incoming substrate is oriented only to one side, and that's where it attacks from. So the enzyme becomes the stereogenic determinant. It imposes stereochemistry limits. Whereas if you were in a flask, you would have both stereoisomers being produced. All right. Regulation occurs with phosphorylase in two different ways. Again, allosteric and then hormonal. But it is a little bit more complex because this is the first time that I'm really going to ask you to think about this in two different tissue types. okay, particularly. So this slide starts off general regulation, and then we have a particular slide that says muscle and a particular slide that says liver, okay? And so in groups of 4, okay? All right, let's see, groups of 4, let's see. 1, 2, groups of, let's see, 4 or 5, okay? Make groups of 4 or 5, and then I'm going to assign you which slide you're going to be preparing to present, okay? And I'll assign one to you. Okay, so show me your group of 4, or show you your group of 5. Okay, that row right there. Okay, we go rows here. So this would be slide 1. You're the slide 2, so slide 2 is muscle. Slide 3 is liver. Slide 1, muscle, and then you guys can be a group liver, and you guys can be muscle. So you prepare muscle. Look at that and decide what's important and why the regulation causes things to be upregulated or downregulated. Where is insulin? In the bloodstream. And so insulin, glucagon, and epinephrine are all hormones that are released in the bloodstream. They hit the surface of the cell, and then they start a cascade of events. Like epinephrine, we know epinephrine binds a receptor, which upregulates a G protein, which separates the separates the G protein into the alpha subunit away from the beta and gamma subunit. The alpha subunit floats over to an enzyme called adenylate cyclase. The adenylate cyclase takes ATP, makes cyclic AMP, makes lots and lots of cyclic AMP. The cyclic AMP will bind to the protein kinase A, and upregulates it, causing a cascade event to occur. And so glucagon and epinephrine are very similar in that. These are part of the signal transduction pathways. Did you talk about those? And did you take cell or biochem? Okay. And so have you gotten to the to signal transduction pathways yet? Ah, okay. Yes. Yep. It's adrenaline. We also call it adrenaline. Uh-huh.
Do they specifically bind to the liver?
Ah, okay. So in liver, there are glucagon receptors. So if glucagon is released, it will interact with liver and make it function. Epinephrine, released upon being excited, okay, the fight or flight, there are receptors in liver and in muscle. And so they will upregulate both of those tissue types. Insulin will actually affect both liver and muscle also. All right? And so, but they're all released based upon a stimulus. Glucagon, when there's very little sugar in the bloodstream. Insulin, where there's a lot of sugar in the bloodstream. And epinephrine, when you get frightened. And so that kind of overrides everything. And so those are the 3 states that we usually compare metabolism. Whether you have lots of food, what your metabolism is going to do, whether you have no food, what you're going to do, and whether if you get really scared, which overrides a lot of other signals. Right, if you eat in 3 days, if you get scared, it forces the body in one direction. All right, are we ready? Who has this first slide? Which groups? Got the front group and got a group there. All right. So, group back there. Why does insulin do what it does on this slide? Well, yeah, why does insulin, and what does it cause?
Well, the reason insulin is regulated is because you have high sugar in your body and you need to go through glycolysis.
Okay, so you need to go through glycolysis when you have high sugar in the blood. Okay, and so insulin will, remember, it's a hormone. It's in the bloodstream. Does it get inside the cell? Does insulin go inside the cell? No, it is going to hit a receptor on the outside of the cell. And that receptor will cause an event to upregulate something in the cell. And in this case, insulin will eventually upregulate a protein phosphatase. Okay? Number one. What does one mean? There's other versions, okay? And the protein phosphatase will then take the existing phosphorylase. What state is this? The active. What does the R mean? Relaxed state. Okay? And it will, a phosphatase does what? Takes off what? Phosphates. And when those two phosphates are removed, I'm in what state? The inactive. And if I'm in the inactive, what do I do to glycogen? Nothing. Okay? I don't want to break my stores of sugar if I have lots of sugar. Does that make sense? Okay. Why does glucagon do what it does in the cells?
Glucagon is like when you don't have sugar, so it's like the opposite of insulin.
So if you don't have sugar, okay,
You want to break down your stores.
you want to break down your stores. Now, what was right next to glucagon here? It said what in parentheses? Liver. Okay, if you don't have glucose in your bloodstream, what is vulnerable? What in your body is vulnerable? The brain and the red blood cells. If your brain stops, is that good? No. Okay, so what will happen is glucagon will be released in the bloodstream. It will affect the liver. Why is not muscle affected? No, it's not because glucagon is stored in the liver. But your muscle has glycogen too. Why does glucagon not affect muscle? There's no receptor for glycogen. So it could be roaming around, but there's just no receptor. Now, glucagon in the liver, when it touches the liver cells, it causes a cascade event and upregulates an enzyme called phosphorylase kinase. Well, what does that enzyme make you think it does? It phosphorylases. Oh no, it phosphorylases. That's great. It places a phosphate on phosphorylase. Places a phosphate on phosphorylase. That's correct. Okay. The enzyme is a kinase. What is it? Kinase? A phosphorylase. And so the substrate is phosphorylase. And so phosphorylase, when this is active, gets a phosphate put on it. Boom. If it is dephosphorylated, it's inactive. If it is phosphorylated, it is active. And this causes what to occur to glycogen? Causes it to break down. In the liver, when glycogen is broken down, the sugar that is produced is intended to be given out to the bloodstream. Okay? What does epinephrine do? And why is epinephrine released? You are scared. Yes. Fight or flight. Whether you fight or whether you flight, what do you need? Energy. And to get energy, you need the starting materials for energy. And so it will take, if the phosphorylase was inactive, it will make it all active, so sugar is able to be broken down. Okay? In the liver, it'll send out the sugar in the bloodstream. What does it do to the glycogen in the muscle? It breaks down the glycogen. What does the glucose do in muscle? If I'm flighting or fighting, what's the glucose going to do? It gives you energy, so I have to go down glycolysis. Okay? All right.
Okay, so if it's already in the active state,
Mm-hmm.
will it just make it produce more?
If it is already in the active state, it will reinforce that. Depends upon how active state it is actually in. So if you've just eaten your big old Snickers bar and you get frightened, most likely all your if you eat a big meal, okay? If you eat a big meal, you're in this state, okay? But if you get frightened after you eat the Snickers bar, okay, the epinephrine will force it over here and you will send out even more sugar, okay? If you're starving, okay, the glucagon is already sending glucose out to the bloodstream, but epinephrine will do this. It will make the muscle now start using glycogen. Muscle in low-fed states doesn't really want to use its glycogen. It wants to conserve energy, okay, because that's a big use of glycogen, so it will try to conserve. But if you give it epinephrine after you're starving, you will still get a burst of energy because the epinephrine forces the muscle to break down the stores that it was trying to save, but now don't save it because I might be dead if I don't fight or flight. Okay, all right. Who did it in muscle? Okay, we got lots of muscles. All right, over here, what is different from what we saw in the previous slide? What is added in this particular case? One thing. The allosteric effector, okay? And so, what is the allosteric effector affecting?
It's affecting whether it's going to be in the T state or TR state.
Okay, the T state and the R state. So the biggest effector here is what? Or one effector here is? AMP. Okay, so what does the AMP do? AMP, well, first of all, is a signal of what? Low energy. Okay, so if AMP is here inside the muscle cell, okay, it can bind to the inactive form. The AMP, this is the inactive state, right? Not breaking anything down. AMP says I'm in a very, very low energy state. If I'm in a very, very low energy state, it will bind to this. It is still not activated by our hormones, but it makes it activated, and it makes it activated a tiny little bit. This is not 100%, okay? It's a tiny little bit. I'm going to start breaking down just a little bit so I don't run out of all ATP, okay? So if you get so much AMP, it's going to shift it over and actually break some of the glycogen down.
So if the AMP is sitting in the active site, how is the glucose going to generate?
It's not. It's fitting in the effector site.
No, but when it's like breaking down the glycogen, how are the glucose molecules?
The glucose molecules are in a different site, most likely a site that is here. And do you see this becomes open in both the active forms and it's closed in the inactive form. So I've got, what I'm showing is the effector site here. What reinforces it to be really, really inactive? One, hormonally, it says I'm inactive, and if there is glucose in the cell, it will bind to the effector site and keep it even lower. Because one, if I don't need to break down my glycogen source, if glucose is flooded in there, and my hormonal state says don't break anything down. Those two things reinforce each other. Okay? And then we talked about the hormonal response, epinephrine and insulin, what it will do. No glycogen on this slide because we're in muscle. Okay, liver. What's different here from those that looked at this slide? What's the different thing here? I still have glucagon and epinephrine making it active. I still have insulin making it inactive. What is the difference in this one? Glucose, right? Okay, so if I have glucagon and epinephrine, okay, and I get this spot hormonally, right? What happens if glucose builds up in the cell? Well, if I've got glucagon, I'm not getting glucose from my bloodstream, okay? But if I've got glucagon going on and glucose is high in the cell, that means it's not transferring out fast enough. So glucose has been broken down from the glycogen, and it builds up in the cell. And what can happen is, even though it hormonally says start, if this doesn't exit fast enough, it can slow it down. This is not 100% off. It's slightly lower because it still hormonally says go. All right? Now, in terms of insulin, insulin will override even this, and it will shut it down, and glucose is let go if it's in the shutdown site, meaning that the allosteric effector site, once it is dephosphorylated, doesn't bind to glucose very well. And so this glucose then can be used to make glycogen, not stored here to keep your phosphorylase inactive. All right. Glycogen synthesis. Let's do the opposite. Okay. And so we're going to synthesize the glycogen. I have to do two really bits of synthesis. I've got to make the alpha 1,4 bonds, which are the majority of the bonds, and then I have to make an alpha 1,6 and branch it. So I need at least some enzymes to do those two things. The activated species that creates the good leaving group for a sugar to be synthesized is UDP glucose. It is a sugar, glucose, that is bound to using UTP as the energy source rather than ATP. Okay? It's synthesized from UTP and glucose 1-phosphate. So what happens is I take glucose from the glycotic intermediate and I convert it to glucose 1-phosphate. We just looked at that in the reverse. Okay? But since it's a equilibrium, I can force it this way. I then react it with the UTP to create the activated intermediate. What is wrong with this mechanism? One, that arrow really needs to attack the phosphate. Okay? Electrons don't attack electrons. And you have to kick up, kick out, kick down. All right? What is given out is a pyrophosphate, which is broken down, which actually provides more energy. So this UDP, 1-phosphate is from the original UTP, and 1-phosphate was from the glucose that it brought in. Okay? This is the activated sugar. Now, the reaction that we just saw was this glucose 1-phosphate plus this UTP to create the UDP. So the last slide was this right here. I have the activated species and I have the growing chain. All right. The enzyme is glycogen synthase. The hydroxide will react with this, and the UDP will be the leaving group. The UDP is in an alpha conformation below the ring. The bond is in an alpha conformation below the ring. So mechanistically, I just cannot have that attack at the top and that fall off on the bottom. It would give the wrong stoichiometry. Not stoichiometry, it would give the wrong stereochemistry. The UDP glucose, the UDP portion has to fall out first, create a carbocation, and then we have an attack by the non-reducing end. The glycogen synthase creates the alpha-1,4 linkage. And it will create the alpha-1,4 and create the alpha-1,4 and create the alpha-1,4 and make long, long chains of alpha-1,4. Okay? Here is a limitation. For this enzyme, the synthase, to work, I have to have at least 4 glucose units as a primer. Well, that is a booger if you're starting from glycogen from scratch. Okay? And so at the center of every glycogen granule, there is a place that provides the primer for this to work. The primer is a protein called glycogenin. Glycogenin is kind of an interesting little protein. It has the ability to add an alpha-1,4 glucose and make a very short chain that becomes the primer. It also is important that one of the glucoses is covalently linked to the protein itself. It will use UDP glucose as the activated glucose source, and so it will add 1 glucose to a tyrosine. There's 1. And it will continue to add glucoses to about 8 glucose units, which is long enough for the limitation of having at least 4 before the glycogen synthesis can start. One interesting fact about this particular protein too, glycogen synthesis, or the synthase the actual enzyme itself, is very active if it is in contact with this protein and works really, really, really fast. But as soon as this protein and the glycogen synthase separates, the activity goes down. Okay? If I'm making a polymer, I can make a polymer very long and very quickly. But that's not how we find glycogen. We find them in little tiny granules because it synthesizes a little bit fast and then all of a sudden it slows down. If by chance it can get back in touch, it'll grow again. And so we make little tiny, very quick branch points, but then elongating it into a really big particle is very, very difficult to do because the enzyme doesn't work as well when it's not touching this granule. But glycogen is not only alpha-1,4s. I actually have to make some alpha-1,6. Okay? The interaction between the synthase and the glycogenin helps limit the size of each particle. The branching enzyme synthesizes that alpha-1,6, but the branching enzyme is really picky. Kind of like Chem21, it has to have the exact thing to work. Okay? And so these are the criterion. It only works on a branch of at least 11 residues. It can work on something longer, but it has to have at least 11 residues, and it transfers a block of 7 residues to an interior site, but it has to transfer away at least 4 residues from any other branch point. Now, it is random in which it actually makes the branching. And so you get branching from somewhere between 6 and 7 residues away and 12 and 13 residues away. But when we describe glycogen, the branch points are on average 1 every 10. Okay? It is not exactly the 10th residue, but it's on average 1 every 10. The overall synthesis here is I take a glucose 6-phosphate and convert it into the 1 using the mutase. I actually activate and form the active species, glucose UDP, which is intended for synthesis. The inorganic phosphate is broken down to provide energy for the process using Hess's law. I will react the glycogen chain, the N terminus of that, or the N terminus of that glycogen chain with the UDP glucose. UDP is the leaving group, and the glycogen grows by 1. This is the alpha 1,4 linkage series. And then the UDP has to be phosphorylated to the UTP so it can activate one more glucose and continue its process. So this is the process to create the alpha 1,4 linkage, which is the majority of linkages in glycogen synthesis. Now, what is interesting about this, to put on a glycogen molecule, okay, and to synthesize it, I start off with glucose 6-phosphate, and I use 1 ATP, and I can add it to glycogen. And when most of it is broken off, it comes off as glucose 1-phosphate, which can be converted to glucose 6-phosphate with no more energy. That means if I put glucose onto glycogen, at least 90% of it, I only lose 1 out of a potential 32 possible ATPs. Now, every 10%, the branch point comes off as a glucose, so I have to use 1 more ATP to get it back to glucose 6-phosphate. So I get 30 of 32 potential ATPs. The efficiency of storage of this molecule, I can get back 97% of all the potential energy by putting a glucose into glycogen. That is a very, very high efficiency rating. We save almost all of the energy and use very little to make it a storage molecule. Okay. Now, glycogen synthase is regulated, and again, take a look. We look at epinephrine, we look at glucagon. And in this case, the glycogen synthesis, okay, if it is dephosphorylated, it is running fast. If it is phosphorylated, it is slow. Okay? Let's go back for just a second. Okay, so listen, the synthase, no phosphates running. The synthesis, if it has a phosphate, it is stopped. Phosphorylase. If phosphorylase is in the dephosphorylated form, it's off. The phosphorylase, if it is in the phosphorylated form, it's on. Exactly opposite. Come on. I'm going too fast for my iPad. That is important. Glycogen synthase. One more. One more. One more. I probably should copy the slide. Okay. Here, phosphorylation is inactive and dephosphorylation is active. All right, what causes this? Epinephrine and glucagon, either I have no food or I'm excited, okay, tends to make it go here, stop synthesis. If I don't have lots of substrate, don't synthesize it. If I need energy to be released regardless, don't synthesize. Epinephrine, again, can also phosphorylate by different kinases. On the other hand, why in the world would I actually make glycogen synthesis go? Well, one, I've got starting material, glucose. Or I have starting material, glucose 6-phosphate. Or I have an indicator that I'm well fed and I'm sending you glucose, start making glycogen. The glucagon and epinephrine stop this, which reinforces the top. Okay? there is what we call reciprocal or dual control. Okay? In this case, we are looking at liver because there's a glucagon receptor. Okay? And so what happens is glucagon will upregulate and cause lots of phosphorylations. Okay? It causes protein kinase A to be active. When protein kinase A is active, the synthase is phosphorylated and the phosphorylase is phosphorylated. Everything is phosphorylated. But in case of glucagon, the synthase shuts down and the phosphorylase starts up. Because glucagon wants you to mobilize glucose for the bloodstream and wants to stop synthesis of it. On the other hand, high blood glucose levels, insulin hits the liver, you start a phosphatase. That phosphatase will take off phosphates off of the synthase and off of the phosphorylase. It inactivates breakdown and it activates synthesis. And if you have lots of insulin, I have lots of sugar, I want to store it. Glucagon, no sugar, cause kinases to activate, phosphorylates everything, causes degradation so that I can send the glucose out. By upregulating one enzyme, either a kinase to phosphorylate everything, or a phosphatase to dephosphorylate everything, I turn on and off the synthesis and the degradation at the same time. So I never have synthesis and degradation going on at the same time. All right? And so, this slide does it really well. I think this slide is a little confusing, but in essence, the last slide said this: glucagon, okay? It will cause cyclic AMP, or sorry, it will cause pKa to go up. It actually, glucagon hits a receptor on the surface of a cell. That receptor will upregulate a G protein. Remember, the G protein is a 3-trimeric, has an alpha, beta, and a gamma subunit. It separates the gamma and beta subunit away from the alpha. The alpha goes to an enzyme called adenylate cyclase. The adenylate cyclase will upregulate cyclic AMP. Cyclic AMP will upregulate pKa. This was an entire chapter that we learned this part. And then what we said was cellular response. Well, now we're teaching you a cellular response. Once the pKa is upregulated, we said it phosphorylates the synthase, turns it off, and we said it phosphorylates the phosphorylase, although it phosphorylates an intermediate, which then phosphorylates this, making it active. So the synthesis is down, the breakdown is up. pKa also will interact glycolysis. It interacts through the enzyme that, remember, is the phosphofructokinase 2, or the fructose bisphosphatase 2, and it will modulate whether I make or break down the 2,6-bisphosphate, which will control the glycolysis. So, glucagon in the liver tends to make glycolysis stop because I don't want to break down the sugar in low sugar glucose. I want to send it out to the other cells. On the other hand, we can have high blood glucose also affects glycolysis. High blood glucose makes glycolysis go faster because I have a lot of starting materials. I want to do synthesis. I need ATP, so it's a time to make ATP. All right.